Good evening to all of you. In today's class, we are going to discuss an important topic called as special purpose diodes. Let me commence this class. Welcome all of you to this basic electronics class. Uh, in this class, let me have a look at the following topics. As per your syllabus, we need to cover up the Zener diode. This is the first topic of our discussion. Then followed by we have a couple of applications related to the Zener diodes. Then we have objectives of the chapter, which is we need to understand the characteristics of Zener diode, and we need to analyze its operation, similar to the PN junction diode characteristics. We need to analyze even here the working principle of Zener diode, followed by the characteristics or operations of the Zener diode. Then followed by we have important relations related to the Zener diode called voltage regulations. So we need to see how Zener diode performs its operation as voltage regulator. So those are the two objectives related to our syllabus. And now we have important key terms that need to be understand. What do we mean by Zener diode, and what are the different breakdown mechanisms that exist in the Zener diode? We'll try to understand these key terms in the following the lecture. Let me proceed with Zener diode. So as we know that Zener diode is almost similar to the working principle is similar to the ordinary PN junction diode, but this is a special diode, of course. A major application of Zener diode is to provide a stable reference voltage. So it is very important. It provides stable reference voltage for the applications that we have across it, and it tries to maintain nearly a constant DC voltage for the application which we connect, which expects DC voltage. So at the end of this sections that I mentioned, you will be in a position to understand the characteristics of Zener diode and try to analyze its operation. The way we do is we look at the schematic symbol of a Zener diode, how to draw it, what is how the symbol, what it represents. All those things we're going to look at. Then we'll look at the breakdown methods. Here we have two types of breakdown methods. One is avalanche breakdown, the other one is Zener breakdown. We'll try to discuss both the breakdown methods. And then we have a Zener breakdown characteristics. What are the levels of current which we need to look at to for safer operation of Zener diode? We look into that through the characteristics. Then we have Zener regulations. Followed by we have Zener equivalent circuits, similar to the PN junction, which we represent it with power supply and the resistance. Here also we have a Zener diode equivalent circuit which we represent it with a power supply and a resistance. And we need to look at the Zener diode from temperature point of view. We represent it with the temperature coefficient. So let us see that what kind of temperature coefficient the Zener diode provides. And also we need to analyze Zener voltage as a function of temperature. We have formulas for those things. And we need to look at what is the power dissipation capacity and derating factors related to the Zener diode. So these are the various topics which we are going to discuss in today's class. Now first and foremost is, let us look at a symbol for a Zener diode. So here we have a symbol for a Zener diode. We have a anode terminal and a cathode terminal. Anode terminal is represented as A and cathode terminal is labeled as K. So this is the symbol of Zener diode, which we have an arrow mark here, okay, and there is a bent line here, as we can see that. The bent line here that reminds a letter Z. The line here which you are seeing here, the bent one, looks like a letter Z, something like this. Okay, if you invert it, it looks like a letter Z here. Okay, so that is the symbol of a Zener diode. So a Zener diode is a silicon PN junction device. Okay. We have given similar definition for PN junction. The even Zener diode is also a silicon PN junction device. It has one junction within that, and it is designed for the operation in the reverse breakdown region. Unlike ordinary junction diode, it's very difficult to operate in the reverse breakdown region, because device will we are going to lose a device. Device is going to be destroyed when you continuously operate it in the reverse breakdown region. But Zener diode is specially designed for the operation in the reverse breakdown region. And the breakdown voltage of a Zener diode is set by carefully controlling the doping levels. So the doping levels and is the Zener diode is doped in such a way that the breakdown voltage is set is decided according to the doping levels. That's very important. And diode reaches reverse breakdown. Okay, voltage almost whenever the diode Zener diode reaches its reverse breakdown, the voltage across it remains as a constant, even though uh, there is a changes in the currents that we look at in a couple of seconds. How exactly the changes in currents maintains the constant voltage across its terminals, and this is the key for the Zener diode operation here. Okay, one of the important feature of Zener diode is whenever we reach the breakdown region, okay, so then it maintains almost a constant voltage across it, but there's a scope for the changes in the current. Okay, so that is the key principle in the operation of the Zener diode. Okay, and now let us have a look at voltage ampere characteristics of the Zener diode, which is given in the figure 3.2. So here we have general Zener diode voltage current characteristics. As we know here, the first quadrant is used for the forward bias. So this is plotted for to represent in forward bias, because the voltage is positive and the current also is going to be the positive. So we have here forward voltage, which is shown along the x-axis, and the y-axis in the first quadrant represents forward current. So the graph of forward voltage to forward current is exactly similar to the normal PN junction diode. We don't have any changes. Still, cut-in voltage, the current is almost zero. Once the forward voltage exceeds the cut-in voltage, typically this value is going to be 0.6 to 0.7 volts. Within this range, the cut-in voltage of a Zener diode exists, and once this we are in this range, the current starts starts flowing. The moment we exceed this, then the exponential current will be resulted here. This is the forward bias characteristics, where applied voltage is positive, current is also going to be positive. But the key operation of a Zener diode is in the reverse region. Okay, so let us have a look at the reverse characteristics, how Zener diode can be operated in the reverse region, and how the breakdown occurs, and the breakdown leads to the maintenance of constant voltage across it, okay, which we call as the Zener voltage. Is the VZ is the breakdown voltage, the Zener voltage, what we call breakdown voltage or Zener voltage is one and same. Once the device breaks down, when we operate it in a reverse bias by changing the polarity across the diode. Okay, though the circuit is not shown here, but we need to apply anode with the negative and cathode with positive. That is the way we can bias. Just if we have a look at here, so if we connect here the anode with the negative voltage, just like this. Okay, so let me show here the anode with negative voltage, positive, negative, positive in this way. So this is the reverse voltage we are. Okay, so we need to keep this one as a variable as we keep varying the reverse voltage accordingly the current changes. Now the question is, what is the reverse voltage we need to maintain it? So we need to reach at least the breakdown voltage. So once the Zener diode is operated in the region called breakdown, which it is represented as a VZ. So then you can see here there is a sudden surge of the current here. The large current starts flowing here. This is the reverse breakdown region. Okay, so it's normal operating region for the Zener diode in the reverse bias condition. So when the Zener diode is operated in the breakdown region, so then we can see here now there's a huge change in the current levels. As we can see, we'll mark it along the y-axis. Suppose if I mark it this one along another current here, so we can see here this is a very big change in the current across the Zener diode, but through the Zener diode, but the voltage change is going to be very small. So here we have a small change in the voltage, but there is a large change in the current. That is the basic principle of operation of the Zener diode. Okay, and if we have to set some limits for this, for which the constant voltage VZ is maintained. Otherwise, so the Zener diode is not it's not meant for to use it. Okay, so therefore, so we need to establish a constant. I mean the we need to operate it in the breakdown region so that the current levels are maintained constant. The current levels are varied to the larger extent here. So that's how the general Zener diode characteristics looks like. So this is the reverse bias characteristics. So let us write it here. This is the reverse bias characteristics. You can see that the current is negative and also the voltage is also going to be negative. So this is the region of operation for the Zener diode. So when we have a Zener diode, it is not good to operate it in the forward mode, but it is right to operate it in the reverse mode, so that whenever V's breakdown region reaches, the voltage across it remains as a V set. Okay, so there's no much change in the voltage, but there is a large change in the current. Okay, let us have a look at the breakdown. So here, what are different types of breakdown methods exist? We'll have a look at once. So Zener diodes is designed, they're designed to operate in the reverse breakdown, as already we have seen that. And two types of reverse breakdown are can be seen in the Zener diode. One of them is avalanche breakdown. The other one is going to be the Zener breakdown. And the avalanche breakdown is basically due to the effect called as avalanche effect. So where an electron which is energized, is going to hit the atom. Okay, and it will try to release the electrons in the outermost band. Maybe the two electrons maybe coming out, let's assume it. Okay, so this is called avalanche effect. One electron, excited electron, hitting the adjacent atom with a lot of energy. So the energy which is absorbed by this atom leads to the release of outermost electrons. Say for example, this two electrons has been released. Again, these electrons get further energized and hit adjacent atoms here, and it may be responsible for releasing additional electrons like this. Okay, in this process, what is happening is more and more electrons get released by the single electron hitting the atom, and it releases two electrons, and these two electrons may release another four electrons. In this way, number of electrons, in the avalanche mode, is going to be increased. Okay, that causes the breakdown, and the breakdown is called as avalanche breakdown here. So there are two types of breakdowns. One is avalanche breakdown, which is due to the avalanche effect, as we already explained the process, and it is sufficiently occurs. The avalanche effect sufficiently occurs at the higher reverse voltage. That's the way we can make a distinction between the avalanche breakdown and the Zener breakdown. Whenever the breakdown happens at the lower voltages, then we can call that as a Zener breakdown. And whenever the breakdown happens for the higher reverse voltage, typically 50 volt, minus 50 or minus 75, so this can be called as avalanche. It may be due to the avalanche effect, and that the breakdown can be called as avalanche breakdown. Okay, so Zener diode at sufficiently higher reverse voltage, they usually break down. So Zener breakdown, as I already mentioned, that occurs in a Zener diode at low reverse voltage. It is called as Zener breakdown, and at high reverse voltage, it is called as a avalanche breakdown. A Zener diode is basically an heavily doped, just not like ordinary diode, and reduce the breakdown voltage. Okay, heavily doped to reduce the breakdown voltage, and this causes very thin depletion region within the Zener diode. And as a result of this, the intrinsic electric field also exists within the Zener diode. Okay, Zener breakdown, the here field is intense, and that pulls the enough electrons from their valence bands, and that creates in turn a current. Zener diodes with breakdown voltages less than 5 volts, that can be called as predominantly is called as a Zener breakdown. The breakdown voltages greater than approximately 5 volts is basically called as avalanche breakdown. So in that way, we can make a distinction between the Zener breakdown and the avalanche breakdown. Typically, a voltage less than 5 volts, if Zener diode breaks down, then it's called as a Zener breakdown. Otherwise, if it crosses 5 volts, and maybe as a given example here, 50 volts or 75 volts, that can be called as avalanche breakdown. Zeners are commercially available with breakdown voltages. So if we want to procure or buy the Zener diode, and they are available with the different breakdown voltages. Typically, the breakdown voltages are less than 1 volt. That's how the Zener diodes are sold, and it's also available with more than 250 volts also. And the tolerance is going to be in the range of 1% to 20% tolerances. That's how the Zener diodes are manufactured. Now let's have a look at breakdown characteristics. Okay, so the figure 3.3 here shows the breakdown characteristics, the reverse portion of the Zener diodes characteristics curve. Already we have discussed both forward and reverse characteristics. And now let us pay attention to the reverse portion of the Zener diode characteristics. And here we can see that the VR is nothing but the reverse voltage. Let us see here, this is going to be the reverse voltage. As reverse voltage, if we start with a 0, and if reverse voltage keeps increasing, what happens here? Okay, as we can see that the Zener reverse current, IR what we call, the reverse current remains extremely very small. As you can see here, when the reverse voltage keeps increasing in the beginning, it remains very small. It's very close to the x-axis. And as this region, you can see here, when we reach the knee region here, the bent region is called as, this region is called as knee region here, where the curve has been reached. I mean, for reverse voltage Vz, the large current surges from the Zener diode due to the breakdown, and that region is called as this circled portion. I can circle here. This is called as knee region here. In that region, the breakdown happens and current starts increasing. Okay, till that the current in the Zener diode almost remains very small. Once we arrive at Vz, when Vr becomes equal to Vz, okay, so let us write it here. When Vr, reverse voltage, which becomes equal to the Vz, as you can see that we reached knee region, and further you can see that current starts increasing. Okay, current surges here. At the moment, if you have a small increase in the voltage, so you'll have a very large change in the current here. Okay. So as we can see here, the reverse current is also called as a Zener current, as we mentioned here. At this point, the breakdown effect begins. The moment it crosses this, the breakdown effect is highlighted here. The breakdown effect begins. The initial internal Zener resistance is also called as a Zener impedance. Zener impedance is represented by ZZ. So let me write it here. ZZ indicates which is a Zener impedance. Okay, Zener impedance is represented by ZZ, and VR is called as a reverse voltage. So these are the key terms which we need to understand from this characteristics. It is a reverse voltage. Okay, and what else we have? So the Zener breakdown voltage is indicated as VZ. VZ indicates Zener breakdown voltage. Okay, that is the representation here. And as we reach this breakdown region, you can see that the voltage almost remains constant. So there is no big change in the voltage in the x-axis if you observe it. Very small change in the voltage in this region. And essentially we can say that the voltage remains constant near the breakdown region. Although it increases slightly, but the current, you can see that the Zener current IZ increases very bigger in nature. Okay. And there are certain levels which we need to make an observation here. The IZK is already labeled here as Zener knee current. So IZK, IZ represents Zener current and K indicates a Zener knee current here. And the other one is the moderate current is IZ is called a Zener test current. This is the normal level of operation. And lower than this value, then you won't see any constant voltage because the current is going to be very small. So as you increase the voltage, then you can see that there is small change in the current, but we don't see any constant voltage across the Zener diode when the current levels are less than IZK. But normal moderate operation is going to be the IZ, and You have a range, upper range of IZM, which is Zener maximum current. Above this, we are going to lose a device because it is not safe to operate beyond IZM. IZM is called a Zener maximum current. So therefore, there are three levels here one need to observe. Below IZK, no Zener operation you can see here, and between IZK to IZM, we can use the Zener operation to the maximum extent. Okay, Zener operation to maximum extent, and above IZM, you can see that the diode we are going to lose a device beyond the IZM current. So therefore, it's not safe to operate Zener diode beyond current with more than IZM. So it is a limit, upper limit is this. So overall conclusion is as long as the current levels remains between IZK and IZM, the voltage across Zener diode remains almost constant, which is equal to Vz. Okay, so lesser than this, the no, stable voltage, which we can see here. So this is the reverse characteristics of the Zener diode. Vz is usually specified at value of the Zener current known as a test current here. So based on this, the Zener voltage is defined here. Okay. Okay. Let us see the regulations here. The ability to keep the reverse voltage across its terminal constant is the one of the key feature of the Zener diode. Zener diode is operating in the breakdown, uh, act as a low current voltage regulator. Okay, because it maintains constant voltage across the terminals. A minimum value of Zener voltage, Zener current IZK, must be maintained in order to keep the Zener diode in the breakdown for voltage regulation purpose. Okay, this is a minimum value as I have already mentioned it. When the reverse current is reduced below the knee of the curve, voltage decreases drastically and regulation is lost. We already told about this. Also, there's a maximum current which we called as IZM, above which diode may be damaged, as I already told, because of excess power dissipation. And so basically, Zener diode maintains nearly constant voltage across its terminals. Okay, for values reverse current ranging from IZK to IZM. A nominal Zener voltage Vz is usually specified on the data sheet at a value of reverse current called the Zener test current. Okay, so this is how the Zener regulations is the regulation is done. Okay, then comes the next topic is Zener equivalent circuit. So let us now go through the Zener equivalent circuits for the ideal model, and later on we will discuss on the practical model. So here we have figure 3.4, which I'm going to show you next. That shows the Zener equivalent circuit. It's an ideal model, and it's a first approximation model of a Zener diode in the reverse breakdown. And its ideal characteristics curve is also shown. It has a constant voltage drop, and its nominal Zener voltage. This constant voltage drop across Zener diode produces a reverse breakdown. And it is shown as a DC voltage symbol. Even though the Zener diode does not produce a voltage, as we can see here. This is the ideal Zener diode equivalent circuit. This is the ideal Zener diode. This is a symbol of a Zener diode. Okay, we have already seen that ideal model. Okay, the symbol, and its equivalent is just it is represented by the voltage source, which is whose voltage is Vz. Okay, in the reverse region, of course, and the characteristics is for the ideal Zener diode is as shown here. Yeah, so here we can see that as reverse voltage is increased, okay, till Vz, the current is 0. Uh, and once as you need to increase the voltage, current is going to be almost 0. But at Vz, as we can see here, uh, the voltage remains constant, but there's a huge drop in the, increased current we can see in this characteristics. Okay, so this is the ideal characteristics curve of Zener diode in the reverse region. When we look into the practical diode model, that's going to be shown in the next curve. So here we have a practical diode, Zener diode model. Let me zoom in that for you. and that's a figure the 3.5 that shows the represents the practical model, and this is called second approximation of a Zener diode, where Zener impedance or it can be called as resistance, and is shown as labeled as ZZ is included here, and whereas in the previous case it's going to be the resistance is not shown there, but here in the practical model the Zener impedance has to be included. Since the actual voltage curve is not ideally vertical, we don't see here as a straight line, perfect straight line. Okay, in the ideal model we have seen that, but here there is a slope, as we can see that a change in the Zener current, which is delta Z, produces a small change in the Zener voltage, which is delta Z. The ratio of delta Z to delta VZ to delta IZ is called as Zener impedance. So here we have a formula. ZZ is called Zener impedance. So let me write it here. This is Zener impedance, which is equal labeled as ZZ, and it's a ratio of change in the Zener voltage, which is delta VZ, to the change in Zener current delta IZ. So that gives us the Zener impedance. And ZZ is defined as a change in voltage or a change in current, and it's a dynamic resistance, also called as AC resistance. And normally this ZZ is specified at a Zener test current, as we have seen in the curve. So here we have this is the Zener test current, as we can see that. So during the mid of this region, we can have a delta IZ, which gives me here. This is the range of where we can measure the change in the Zener current, that gives me delta IZ. And correspondingly, if you extend it to the uh, negative x-axis, that gives me delta uh, corresponding to changes of this gives me this voltage, and change of this current here, the second level or lower level, gives me the another voltage here as a lower voltage, and I mean higher, more negative voltage here. So this gives me delta VZ, and if you take a ratio of delta VZ to the delta IZ, that gives me the Zener impedance. Okay, this is an AC resistance, and it is generally specified in the test current region here. And it's best to avoid operating Zener diode near the knee region. So here this is not a good region to operate the Zener diode, because here we won't see any uh, Zener operation, because the voltage has to be, voltage, if you operate it here, so the voltage is varying to the larger extent, and the Zener diode loses its operation here. Okay, so impedance changes dramatically, if you go in this area. So therefore, so it is better to operate in the test region. Okay, so here we have a Zener diode equivalent for the practical model. So as usual, the first one shows the Zener symbolic representation, as we have seen here, a Z symbol on the top of this arrow mark here. This is the Zener diode symbol, and its equivalent practical model contains a voltage as VZ across it, across the both the resistance, and the impedance is also shown for the practical Zener diode model. Okay, so this is a characteristics curve, and here we show how to measure even the Zener impedance, and here we have both the practical model equivalent circuit. Okay, it's good to operate the Zener diode in the test region, so that we can see the Zener operation properly here. Let's go through the example here. One example that illustrates whatever we have discussed here in the previous section. A Zener diode exhibits a certain change in VZ for a certain change in IZ on a portion of linear characteristics curve. This is a linear characteristics curve between IZK and IZM, as illustrated in figure 3.6. What is the Zener impedance? So we have to see that all data which is given in the characteristics, by looking at these characteristics, we need to calculate what is the change in the what is the Zener impedance, which is ZZ. So we already know the formula for Zener impedance as delta VZ by delta IZ. We need to estimate what is the change in the Zener voltage to the change in the Zener current. So here the lower limit is 10 milliampere and upper limit is 15 milliampere. The change in this is going to be the delta Z is 5 milliampere. Similarly, if we extend that to the x-axis, we get a change in voltage as 50 millivolt. So therefore, according to the formula, delta Vz by delta Iz, if we substitute 50 millivolt by 5 milliampere, that gives me a Zener resistance or Zener impedance as 10 ohm. This is how we need to solve the problems related to the Zener diode. Next, we have a temperature coefficient, which is an important parameter. We haven't seen this temperature coefficient with reference to ordinary PN junction diode, but here it's a good to uh, look into the parameter called as a temperature coefficient. So the temperature coefficient, it specifies the percentage change in the Zener voltage for each degree Celsius change in the temperature. Okay, that is the definition for the temperature coefficient. It's a percentage change in the temperature. It's a percentage change in the Zener voltage for each degree Celsius change in the temperature. Let us look at an example here. A 12 volt Zener diode, 12 volt is Vz, okay, is given as a 12 volt. It's a breakdown with a positive temperature coefficient of 0.01% per degree Celsius. Okay, this is the temperature coefficient it is given, and that will exhibit 1.2 millivolt increase in the Vz when the junction temperature increases by 1 degree Celsius. When the temperature changes by 1 degree Celsius, then the voltage change will be Vz will be increased by 1.2 millivolts. Okay, that is the positive temperature coefficient of resistance. The formula for calculating the change in Zener voltage for a given junction temperature change for a specified temperature coefficient is as shown here. This is the formula which we need to remember here. Delta Vz, which is a change in Zener voltage, is related to the Zener voltage or breakdown voltage, what we call. And Tc is nothing but it is the temperature coefficient, which is generally specified as in percentage per degree Celsius change, as we have shown here. And delta T is going to be the change in temperature here. So these are all things which is defined here. So Vz is the nominal Zener voltage, okay, at the reference temperature 25 degrees Celsius, and Tc is nothing but which is a temperature coefficient, and delta T is nothing but a change in temperature from the reference temperature. Reference temperature is already given as 25 degrees Celsius. And now let us go in detail and see that a positive temperature coefficient means Zener voltage increases with the increase in temperature. Okay, so or if decrease with the decrease in temperature. We should not look at only the increase in temperature. A positive temperature coefficient means Zener voltage increases with increase in temperature, and or Zener voltage decreases with the decrease in the temperature. That is the meaning of a positive temperature coefficient. A negative temperature coefficient is just opposite of what we said here. Means the Zener voltage decreases with the increase in the temperature or increases with the decrease in the temperature. That is the meaning of negative temperature coefficient. So in most of the cases, though we give temperature coefficient as 0.01 percentage, uh, per degree Celsius. Okay, but in some cases, temperature coefficient is expressed as millivolt per degree Celsius rather than percentage per degree Celsius. For these cases, the formula is little bit is a small change. So delta Vz now changes to Tc temperature coefficient into our temperature coefficient is mentioned as millivolt per degree Celsius instead of percentage per degree Celsius, and delta T is going to be the change in temperature from the reference temperature. So using this, we can calculate okay the variations in the Zener voltage as temperature is changed. Okay, so here we have a one problem. Let us look into the example 3.2. An 8.2 volt Zener diode. Okay, 8.2 volt is specified at 25 degrees Celsius, and it has a positive temperature coefficient of 0.05% per degree Celsius. So here the Tc is given to us, which is 0.05 percent, and here we have an Vz, which is 8.2 volts, and it is asked here what is Zener voltage at 60 degrees Celsius. So we need to calculate the Zener voltage at 60 degrees Celsius. So now let us go through the formula. The change in Zener voltage is given by delta Vz is equal to Vz into temperature coefficient into delta T. So Vz is now it is 8.2 volts at 25 degrees Celsius, and the temperature coefficient of resistance is given as 0.05% per degree Celsius, and the change in temperature is given as the the reference temperature is 25 degree and what is expected is at 60 degrees Celsius. So change in temperature is 60 degree minus 25 degrees Celsius. If we simplify this and do some calculations, that gives me delta Vz change in Zener voltage as 144 millivolt. From 25 degrees Celsius, if temperature changes to 60 degrees Celsius, then the change in Zener voltage is going to be 144 millivolts. Okay, so 0.05 per degree Celsius was converted to the point, it is in percentage, just divided by 100. So it becomes 0.0005 by per degree Celsius. The Zener voltage at 60 degrees Celsius is nothing but Vz plus delta Vz we can add up together, and that gives me 8.2 volts plus 144 millivolts, which is a change in delta Vz, that gives us around 8.34. So what is the conclusion from this? At 25 degrees Celsius, the Zener voltage is 8.2 volts, but when the temperature changes to 60 degrees Celsius, so the corresponding change in the Zener voltage is 8.34 volts. Okay, so this is how the problems related to Zener diode can be solved. Now let's go through the Zener power dissipation and the derating factor. This is another important parameter of the Zener diode. All diodes are rated by the manufacturer for absolute maximum ratings. Recall that the DC power dissipation is the product of voltage drop into the current. Okay, so this is a product of voltage drop and current. For Zener the voltage drop is Vz, and the current in the device is labeled as Iz here. The power dissipation is simply the product of Vz into Iz. Okay, so the maximum power dissipation is designated as PD by the manufacturer. Let us take an example of commercial Zener diode, 1N746 Zener diode, and for a maximum power of 500 milliwatt, that is the PD which is given, and the for the another device which is 1N3305, the PD is 50 watts, which is a power in high power. Okay, Zener diode. So this is how the power dissipation of a Zener diode is mentioned. It's just a product of voltage, Vz and Iz. Okay. Now let us look at the power derating. What do we mean by that power derating, and how to use it in our Zener diode calculations. The maximum power dissipation of a Zener diode is typically specified for temperatures at below or certain at or below a certain value, say 50 degrees Celsius, for example. Above the specified temperature, the maximum power dissipation is reduced according to the derating factor. That's where the derating factor comes into the play. The derating factor is which is expressed in milliwatt here, milliwatt per degree Celsius. That is the derating factor, and the maximum derating factor can be determined with the following formula: PD derated equals PD, which is the maximum power dissipation, minus the power derating factor, which is milliwatt per degree Celsius, and that's multiplied with the change in temperature. And let's have a look at this problem so that we can understand how this derating factor is going to be useful. A certain Zener diode has a maximum power rating of 400 milliwatts at 50 degrees Celsius, and the derating factor is 3.2 milliwatt per degree Celsius, and determine the maximum power the Zener can dissipate at a temperature 90 degrees Celsius. So what is asked in the problem is maximum power dissipation is given, which is at 50 degrees Celsius, which is a 400 milliwatt, and derating factor is given 3.2 milliwatt per degree Celsius, and we need to estimate what is the maximum power that Zener can dissipate at 90 degrees Celsius. Let's use the same formula which we already mentioned. PD, the power dissipation with the derating factor, is equal to PD minus the derating factor multiplied with the temperature. So PD is given as 400 milliwatts. So this is 400 milliwatts. This is the maximum power dissipation, minus derating factor is 3.2 milliwatt per degree Celsius, and temperature changes 90 degrees Celsius, minus this expected the temperature power dissipation, and this is the reference temperature, and that gives me If we simplify that, that gives us around 128 milliwatt, and that we subtract from 400, that gives us 272 milliwatt. That's going to be the PD rated. Okay, so in this way, the any problem okay, related to the power derating can be solved. There's a related the problem which is given here. I look forward for the students to solve this problem. Okay. Any questions? I think we have ended up the Zener diode, and now it's only the Zener diode data sheet is given, and I look forward for the students to go through the uh, different commercially available Zener diode data sheets. And in the next class, we look at a couple of Zener diode applications, okay? General applications of Zener diode. With that, we have come to an end of today's class, and next class we'll cover up Zener diode typical applications here.